Hi guys, Dr. B here. This is topic 1.6 photoelectron spectroscopy, or PES. We talked about mass spectroscopy already, and now we're going to look at something else called photoelectron spectroscopy. The objectives for this topic is to be able to explain the relationship between the photoelectron spectrum of an atom or ion and the ground state electron configuration of the species, and the interactions between the electron and nucleus. I know it's a lot here. Photoelectron spectroscopy is an experimental technique that measures the relative energies of electrons in atoms or molecules. It works by ejecting electrons from materials using high energy electromagnetic radiation, like UV radiation, and then measuring the kinetic energy of these electrons. This is called photoionization. We're going to be looking at graphs, and they show the relative number of electrons and their corresponding binding energy. The binding energy can be described as the amount of energy needed to remove an electron from an atom. The electrons with the highest binding energy are the ones that are going to be closest to nucleus because they have the greatest Coulombic attraction. So Coulombic attraction, it's all related to Coulomb's law. Like I said, it's going to be your best friend, hopefully. All right. So the PES graphs directly correspond to the electron configuration. So we see this is the full PES for sodium. The x-axis is often set up to indicate the amount of ionization energy, and usually it's set up from left to right, meaning the higher ionization energy is on the left, and on the right side it decreases. However, they can flip it on you, so you have to be careful that you're reading it correctly. The highest value for the ionization energy is the innermost electrons. So here the highest, the strongest peak, if you will, is on the left. Because we know that there are two electrons in the 1s orbital, we can assume that that height, we can use it to kind of guesstimate the other ones. So for example, just by looking at this PES, and we're going to assume that the 104 megajoules per mole, that's going to be the 1s2, so the same height is going to be for the next one, it's going to be another, that's the 2s2. Then you notice that it's the next one afterward, the third peak is 3 times the two of them, and all that type of stuff. So that last one over there is half of the 2, so it's 1. So 1s2, 2s2, 2p6, 3s1. So something you're going to have to be able to do is look at a graph and then recognize what element it is and what is the electron configuration. Which element is represented below? So this is the full spectrum for this particular element. Sometimes it's going to be a spectrum that only shows the valence shell with valence electrons. So the way that we're looking at this, if this is the full one, this has to be 1s2, where I circled first. This is 2s2. This is going to be 2p4. So it's going to be oxygen. Which element is shown below? Again, so this is the x-axis is different than the first example I showed you earlier, because now the x-axis is red from right to left, meaning on the right side is the stronger ionization energy. So be careful with that. So this is going to be still 1s2, 2s2, 2p6, 3s2, 3s2, 3p1. So 1s2, 2s2, 2p6, 3s2, 3p1 is going to be what? What's it going to be based on our periodic table, knowing how to read these? This one is going to be aluminum. That's probably not how I spell it, but it's close enough. So one of the questions they may ask you, based on this the absorption spectra, what is the ion that's going to form, etc. So it can be used. This information can be used to answer another question, or it can even say, based on the absorption spectra shown, what formula will this element make with oxygen in an ionic compound? So you have to be mentally prepared for that. All right, if you have any questions, please let me know. Thanks. Hit that like and subscribe. Bye.